So from the introduction, you can see that the usefulness of transistor. So here I want to explain the principal function of a transistor. Before I show the component, the material used to make a transistor. Okay? So see the function first. So what can a transistor do? Actually, there are many types of transistors. So I'm going to show the first one, a very simple one, which has symbols like this. Okay. So there are terminal we use a term like collector, emitter, and base. Yeah. This one is called a bijunction transistor. Okay. Another one is for power actually. So I should explain more about the one which is used in power electronics. That is called MOSFET. Yeah. MOSFET FET come from field effect transistor. For this one is about like material things. So and symbol is like this. So the label for the terminal is like this. This one is source, this one is drain, and this one is gate. So you can see the same three terminal for bijunction transistor, and for the MOSFET, or sometimes we just call FET. Okay. You can see the different. Even from the schematics, you can see the difference. The difference is that for the control terminal, this one is, yeah, we can say this is control terminal. You can see that for bijunction, the control terminal directly connect to other terminal. You can see that. It means current can flow this way when turned on, and current can also flow this way, right? Like this. But for this one, there's no current flow this way, because you see the disconnection here. So that's why it's called field effect. It just uses the field to turn on. But this one you need to use the current, small current inside here to turn on. This one just uses the field. That's why it's called field effect. And so the principle of the function is that when you do not apply voltage between G and S, okay, let's say because this is ground, the symbol means ground. So if VGS connect to ground also, it means V voltage between G and S, in this case VGS equal to 0. In that case, even though you connect this one, the drain to battery, let's say you connect it to battery like this, you connect like this, still there's no current flow this way, right? But if you connect G to positive polarity of the battery like this, then it introduces an electric field inside here, then current can flow this way. That's why we call it electronic switch. You want to switch on or off, you need to send the signal through the gate. And the signal that you need to send can be from the battery itself or can be just from microcontroller. Like for example, something like that has chip. Okay, and then you can program to send a signal from its terminal, let's say like this. Of course this one also has ground, right? So you program send signal here like to switch on as you output digital voltage like 5 volt or 6 volt, 5 volts mostly, then you can turn on this one. Okay, so in some sense you can control it by microcontroller. So you program the task for the transistor to turn on or to turn off, something like that. Okay. Yeah, only this you can, it became the revolution of electronics, just electronic switch. Yeah, because this kind of transistor can be used to build a logical gate and also build power electronic components, okay, amplifier, all kinds of electronics. And before, actually researchers in the past already knew that the electronic switch is the key ingredient for revolutionizing the computation and power electronics. That's why researchers try to find what kind of material can be used to build this kind of electronic switch. Yeah, actually before this electronic switch, researchers use mechanical switch, vacuum tube switch, and it's very big, just one switch. The size is like maybe not less than this one, just one switch. That's why IBM computer in the past has the size of like this room, because that time they use mechanical switch, vacuum tube switch, and it's so big.
So it's like quantum computer?
No, quantum, it is very different. It uses quantum theory on very, very small device, even smaller than this, smaller than electronics transistor, something like that. Any question?
For the BJT, because you get like collector, emitter, and battery. So my question is, it controlled by current or voltage. When we connect the wire to the big gate, voltage and current we go to integrate and separate.
Yeah, actually, to turn on BJT, you need enough current. Okay. Or can say that actually the current flow from collector to emitter proportional to the current flow from B to E. So sometimes even though you have large voltage, but your system itself can produce very small, can uh, supplies very small current, then the current flow from C to E also not so big. Okay, so the next part would be about the material that can be used to make the transistor. So I'm going to show the next slide, the next file. Okay, so this lecture is about semiconductor components. It's about the material that is used to make a transistor. So here the contents, there are around 7 points. Yeah, 6 points. So first of all, I want you to know some definitions. The first, ideal components. So what is the meaning of ideal components? You can see the term here, power dissipation is 0. Let's say you have a resistor. What kind of resistor that dissipates 0 energy? What value of the resistor? I mean, value of the resistance. Okay? A resistor has a resistance. Let's say you have a voltage. Okay, I can write this DC voltage supplied to a resistor like this. So my question is, what the value of resistor should be in order to not to dissipate any energy? 0. So if resistor is 0, it does not dissipate any energy. Okay. Any other value?
I think the higher value of the resistance, the lower power dissipation.
So how about infinity resistance? Because if we have a very light resistance, then there's no current. So if no current, no energy dissipation as well. And this one also correct. If you don't have any resistance is 0, I mean there's no friction.
Just so but when the resistance equals to infinity, it's like it was a switch.
Switch where?
Equal to infinity.
Yeah, it's like we have an open switch, right?
Yeah.
Right, correct.
Yeah.
So if you turn it off, turn the circuit off, of course there's no energy dissipation. So ideal components means like this. Let's say your MOSFET is, if you consider it as ideal, when it conducts the current, the resistance is assumed to be 0. If it has some resistance, it's gonna burn up, it's gonna dissipate energy, dissipate heat. So actually in practice it's very critical thing, critical when you try to turn on and off MOSFET, if you don't turn it on completely or you don't turn it off completely, MOSFET is gonna burn. See? So, but in theory, we don't care about the practical things yet, and we just assume that the components are ideal, right? but not completely ideal. For example, if you say a wire, you need a wire to be big enough in order to have zero resistance, but actually it's not exactly zero, right? It's just some small resistance, but it's okay as long as it's not going to burn out the wire itself. The next definition is about unipolar component. So here it states that only one type of mobile charge, electrons or hole during the current flow. You're gonna see what is the meaning of holes later. And for unipolar component, there's more losses of energy. Okay. Another one is bipolar components. So in here it states that two types of mobile charge during current flow, which means the flow of holes or the flow of electron. Okay. Okay, another terms about power electronics. So you categorize the system is power electronics if in application the voltage is larger than 100 volts and the current larger than 1 amp. Because if it's very small current or very low voltage, it's just like electronics, mostly for the signal processing, for digital thing, computation or something like that. You don't need to call it power electronics. Okay, microcontroller itself, inside that, you don't need to consider it as power electronics. That's why when you buy component like small buck converter, boost converter, and all kind of thing used with the small electronic, you don't need to care so much whether it's gonna be burned out or some component is gonna be broken or something like that. You don't really care. And in power electronic system, there are huge losses. Just 1 meter square, the losses can be up to 500 kilowatt. So that's why some the power electronic component like MOSFET, in many cases you need heat sink to help dissipate energy. Otherwise the temperature in the MOSFET increase too much and the property can be lost. If we compare with the radiator of a car, you know this? In front of the car, you open the cover at the front, you can see this radiator. Actually it can dissipate energy, power around 1 kilowatt per meter square. Okay, and now we come to the material or element used to make semiconductor. Okay, so here is the element, and we need to take some element, do some process in order to make a semiconductor, and we need to assemble the semiconductor in a certain way in order to make a transistor. Okay. And so the base material is silicon. The silicon in this group has the how many electrons at the most outer layer? How many electrons? Yeah, 4. The most outer layer, it has 4 electrons. And yeah, actually only silicon we cannot make it to be a semiconductor, right? There are more explanation at the next slide. Yeah. Okay. So actually, in order to make it become a semiconductor, we need other material to mix with silicon, and we need element in this column and element in this column. So for this column, how many electron of the most outer layer? Yeah, 5. 5. This one has 4, and this one, yeah, just 3. Okay, just to see, to learn more about the conductivity of this material. Yeah, just to know the term insulator. Insulator means the material does not conduct electricity. For example, like non-metal. For metal, yeah, it's kind of conductor. It can conduct electricity. And there is also the material that in between. Okay, if you modify, or you you make a little synthetic and operate it in a certain condition, it can conduct electricity. Okay, something like that. And also for the conductivity condition for metal, if the temperature is high, the conductivity become low. Okay, so it means the higher the temperature, the more resistant, something like that. But for the semiconductor, the higher the temperature, the better the conductivity. Okay, you can see here. Well, so come back to here. How do we use this the material in this column and material in this column with silicon to make a semiconductor? Actually, here is the key. For the silicon, yeah, the most outer layer has 4 electrons. So if only silicons, you can see that it can just bound all like this. The electron bound from one atom to another. So and this bond is called valence bond. Okay? So there's no excessive electron, because all electrons are in substance already busy with something, cannot do anything else. Let's say. But if you dope the silicon with the phosphor that has 5 electrons at the most outer layer, then there is 1 free electron. So this electron is not busy in some sense. And if you dope silicon with another element that has 3 electrons at the most outer layer, then it's kind of it has a hole, it means attraction of electron. A hole here is an attraction of electron to complete the valence bond. So this one is called a negative type or n-type or electron type of semiconductor, and this one is called a positive type, or sometimes just call it holes, because hole here means not enough electron, so it attracts electron. So if we take n-type and p-type and join together, so here is p-type and here is n-type, right? So p-type actually attract electron. Okay. N-type has free electron. Okay. So when you okay, let's see. Yeah, when you join together, electron from this side attract to this side. So it has, if we look at the charge, the p-type have excessive charge, right? So the valence bond attract electron, but then when electron come here, if we sum all the charge inside here, because in the nucleus also have positive charge that equal to the negative charge. So actually, without electron flow from this side to this side, the charge is just zero, right? This one also zero, this one also zero. But due to the force of valence bond attract more electron, and then they become negative charge. Okay, it's like this. Okay, and so then if you apply voltage, okay, to the semiconductor here, if you connect the negative polarity to the p-type and the positive polarity to the n-type like this, what happened? So what happened? What happened is that the accumulation of negative charge more in here, more inside here, right? More inside here. And accumulation of positive charge more inside here. So this part is called depleting zone. So if more negative charge accumulate here and positive here, how to say? Electron come to this way. So in some sense, this one has positive because electron, the free electron inside here flow this way. So electron inside here run out. Okay, electron inside here run out. So there cannot be electron flow in a circular like this. At some point, electron in here just run out. So in this way, it cannot conduct electricity. Okay. And if you reverse the polarity, so the positive polarity connect to the p-type and the negative connect to the n-type. So this one has excessive electron, right? And this one try to attract electron. So this one attract electron from here to here, and this one supply more electron here. So in this way, it can conduct electricity. Because this part is not going to run out of electron. Because electron can obtain from the negative polarity of the battery. Yeah. You have any question? No? Yeah? Okay, so anyway, this is just some principle. Maybe you don't need to reinvent the wheel, no need to, because our focus is power electronics, not really on the material. This is just to show you how researchers in the past came up with some good idea to make this kind of thing. And then the next one, we call it metal oxide semiconductor effect. So metal oxide semiconductor is MOS. This one actually, metal oxide here, silicon oxide here is used as an insulator between the gate and the junction of P and N. This one is transistor. To be precise, it's MOSFET. So the term MOS is metal oxide semiconductor actually because of the insulator here, silicon oxide used as insulator between the gate and the junction. Because insulator in between conductor, then it can only produce the electric field but cannot allow the current to flow, right? And that's why we call it the field effect here, term here, field effect. So here I will try to explain quickly because we just need to know the functionality of the material or the components. So in order to open the gate to attract, we need to supply voltage that need to be greater than some certain threshold. So this is just a part of the gate because wait here, just around here, okay. I should remind. So this one is P type. P type means it has more hole. Okay, hole. N type has more free electron. Okay, more free electron. So when you supply voltage here, this is oxide. This is plus, this is minus. P substrate. Yeah. For in this case, no conductivity. This one is just accumulate charge but cannot conduct. But in this case, it can conduct. Yeah. So we just need to give the positive voltage from the gate. So the positive from the gate will attract electron to come here. So when there's not enough electron here, and this one also has excessive electron, and then it can allow the current to flow like this. Okay, so an electron flow from source to drain, or you can say the current flow from drain to source, something like that. So let me draw the schematic of this MOSFET. We have this one is drain, this one is source. Okay, this is gate. Yeah, that's why when you see if you notice the MOSFET here, you see the three terminal like this. Okay, three terminal like this. So actually, if you look at here, you can see that the three terminal like this, right? That schematic you draw like this. Now let me recall the term ideal. So when you want MOSFET to work in ideal case, when you want to switch on, you need to supply voltage to a certain level in order to turn it on completely. For example, at least 6 volts but for some particular MOSFET, because there are many type, many model actually. So let's say that for this MOSFET you need VGS to be larger than 6 volt in order to turn it on completely. If you don't turn it completely, there are some small resistance there, and that resistance, it's like friction, it is gonna dissipate energy, and over time it can destroy the property of this transistor. And when you want to turn off completely, because here you have a oxide, metal oxide here as insulator, so in some sense it's kind of it behaves like a capacitor. If it behaves like a capacitor, let's say if you drop the voltage to 0, maybe it cannot turn off completely. What I'm trying to say is that, well, if you add another slide here. Let's say you have a resistor like this, and then you have a capacitor, just simple one. This is one is resistant, this one is capacitor, and let's say you want to switch on and off via the MOSFET, okay? But inside the MOSFET it has a property of, it has small resistance and it has a small capacitor. This is type. Let's say when you want to turn it on, this one is VGS, let's say, and then you want to turn it off, let's say you give it a 0 voltage. So it should be like this. If you want to give it 0 voltage, it should be like this. So switch on here, full voltage, switch off here. No, this is wrong. Yeah, like this. Eh? No. Like this. Full voltage, 0 voltage. Right? Yes, like this. Yeah, if you still remember property of first order system, dynamic control system, in modeling it's first order differential equation. The voltage that charged to capacitor would be something like this, and then something like this, right? Yeah. So it switch on and off very fast. The discharge is not fast enough. You got the point? The discharge is not fast enough, so you cannot turn it on or off completely in this case. Yet this one may be fine, but this one can be bad. I mean, for the for the practicality, you may burn the MOSFET. So sometimes most of the MOSFET has to be function like this. You give it maximum voltage, but then you want to turn off completely, or you want to recharge fast, so you something like this. You need to VGS has to be negative, okay, something like that. But because this one cannot, and we need a complete model in order to explain this. So anyway, you just got some idea that the problem that may occur is that if you don't find a way to turn on or off completely, you cannot say that the component perform in the ideal case. If not in the ideal case, it may dissipate energy. It's okay if you have the heat sinks good enough and can release energy on time. That's good. But otherwise it's gonna be broken. But also you need to look at the functionality. If it cannot turn on or turn off completely, then the system still function as we expect or not. The whole circuit function as we expect or not. Okay? There's another problem. Yeah. Yeah, so I want to finish at this point. I will continue to explain other type of transistor in the next lecture. Okay, but if you have any question, feel free to ask.
Mr. Charles, how about in F equation, we have we should to take GF figures that 6 voltage. Wait.
Here, VGS.
So why? Because we want to use the resistor. Why we
Actually, when the current flow from drain to source, and in order for this component to function as ideal case, we need it to flow freely. Flow freely means no resistance in here. So it can flow freely if the field here is strong enough. The field here. Oh, I think this is a mistake. Like this. Oops. Yeah. So the field here must be strong enough in order to have enough electron in here to make a bridge for current to flow. If not enough electron, then the flow is not. It's like there are obstacles in order to flow through this bridge. So if there's obstacle, I mean there's resistance. And actually, the bigger the better for some MOSFET, some driver to drive the MOSFET to turn on and off, they can use up to 12 volts. Okay, something like that.
So, in this curve, we are want to make the semiconductors.
Yes.
And we can make semiconductors in ideal components, or we can make semiconductors in any case.
Well, so to make semiconductor, okay, we need to select material and do some process correctly and assemble it in a proper way. Okay, this is one thing. And then when we want it to operate in the safe zone. In the safe zone means just like we consider as ideal case, which means resistance should be zero, nearly zero, or should be infinity. So when we switch off, we want the resistance here is infinity. And when we switch it on, we want the resistance here to be zero. Something like that. So to switch off completely, or to switch on completely, you need a field here to be strong enough. Okay, now I got it. So the voltage on the capacitor here, if you switch on completely, you need this is high voltage, so the voltage at the capacitor here also fast, right? I mean also large. So the field is strong enough. And then if you want to switch off completely, you also need field strong but in reverse polarity. So if the field in reverse polarity, it switch off completely. Like that. Okay. So in here, the field, if you don't supply a negative voltage like this, the voltage in capacitor is like this. It's still positive, right? Here, like here, this side, it's still positive. So in some sense, it cannot switch off completely, and that is bad. In that case, very bad. Yeah. Well, so here voltage like this, voltage and capacitor like this. So it's reverse polarity. Then it can switch off completely. Okay, so I think it's all good for today. I'm gonna stop now.